Okay, what's DF? Does that look familiar? It's one of the big things you got to take out of a calculus course, because one of the most important things in the calculus sequence. Again, it's something that I find people come out of calculus unfamiliar with. Okay? And I haven't, the last, I taught in class and distance calculus courses for years, but now I'm in the second year calculus sequence. Haven't taught first year calculus in quite a while. Will has a nicely arranged course that he likes to teach, and I, of course, enjoy teaching these, so it works. But I haven't had an in-class first year calculus for maybe a couple of decades. Okay, probably just one decade, somewhere back in the second preceding decade I did. I used to teach it a lot. So I don't know why this is falling through. Okay?
I think it feels like it was just a notation thing. I didn't recognize that notation. Yeah.
Yeah, well, you really have to recognize that notation.
Yeah.
I mean, it's all involved with the whole concept of, you do geometrically. The slope, the tangent, the equation of a tangent line to a curve at a point, and so forth. It's completely related to that. Okay? So anyhow, now we can kind of do a little fuzzy math with the notation. You know that, I'll say sort of, because df dx equals 2x, right? Now df and dx are not algebraic quantities, so we can't really multiply by dx. But if you look at the geometry of tangent lines, you make sense out of this. Okay? So that's kind of all there is to it. Except that, and this is something that I really want you to kind of wrap your heads around now. One of the few things that you do in multivariable calculus that is sort of important for differential equations is the differential of a function of two variables. Okay? So we could define it. Okay, df equals f prime times dx. Write it that way. Because df dx equals f prime, and if we accept this, which I'm not going to go into detail on now, but it's very much related to what you did for homework, projecting tangent lines. Okay? We could write this, okay? Now, this is if f is a function of x. Okay? Now, if f is a function of t and y, then df equals the partial derivative of f with respect to t dt. And I'll tell you what partial derivative is. It's not hard to understand, at least how to calculate it. It's this. Okay? Now, we could think of f prime. F prime is the rate of change of f with respect to x. You take the rate of change of f with respect to x, multiply by the change in x, and you get the change in f. Okay? And that's probably actually worth writing down. ROC for rate of change of f WRT with respect to x. So f prime delta x is the approximate change in f when x changes by delta x. And there's a simple picture for that. That should be very familiar to you if you wrote out all the details of what you did for homework, right? You're smiling. You recognize something. First time. No, it's not the first time. It won't be the last. Okay? Delta x, the slope is f prime, and here's your delta f, the change in the value of f. And I'm not using delta y here because I've got y's up here. We don't want to get too confused, but that shouldn't give you any trouble. That's the basic picture of the what I call the fundamental triangle, which my pre-calculus class is going to see. And C and C and C this semester. Because how do you learn calculus if you don't understand that? Yeah, you can learn it. You know, if all you're doing is doing manipulations, you can learn to do the manipulations. It's much easier to learn to do the manipulations if you've got the picture. But people do manipulations without the picture all the time. Because for some reason they think that's easier. I know it's not, because Will doesn't do this. And I very much doubt it's because Ms. Kaiser doesn't do this. Okay? You're told this, but then you grab on to whatever's expedient for the assignment. Okay? So you get the assignment done and you never get it into your gut. So, one thing I hope you learn in this course is how to get things into your gut so that they stay with you. It's not easy. Not easy at all. You got to keep beating that drum. Okay, so anyhow, now we got this. Well, if you understand this statement, this is just the rate at which the function changes for a change in t, and you multiply that by the change in t, but y also causes it to change, and you multiply that by the change in y. Okay? So this is because now you got two variables. Okay? So that's a little bit of multivariable calculus, but it's a real easy part of multivariable calculus. How that applies to this thing or this thing. We're gonna have to wait until winter. Oh, incidentally, I've got to get you guys to fill out drop ad forms.
Yes.
So let's make sure, yeah, I mean, we can still do it next week, but let's get it done. I think my dean has created the differential equations course, but with the power outage yesterday, I'm not sure. That kind of threw everything into flux. I emailed her in the morning asking her to do that, so, we'll see. Okay, so the change in F is equal to the rate of change with respect to t times the change in t plus the rate of change in y with respect to y. Actually, I'll even show you this a little bit. Okay, so like t's this way, y's this way, right? Now, let's use this one. Okay, if you go in this direction from this point, you got a little bit of a slope, right? Multiply that slope by the width of this thing, it tells you how much it changed. In this direction, you got a change in, say, y's here, so y changes, right? And there's a slope in the y direction. And you can kind of visualize that little triangle right there, right? So you got the change you get here plus the change you get here equals the change you get here. As long as this is a perfect plane, but if a general function f of yt, there's a little change in these derivatives, little change in these slopes between here and here. So this slope is not necessarily exactly equal to this one. This is not exactly equal to this one, right? So this, you only get, if you add these two changes, you're only getting an approximation to this change. Okay? So that's what we're kind of thinking about, because you're going to have to think much more deeply about all the implications of that when we do multivariable calculus. That's really what we're seeing here. Again, the rate of change with respect to t times delta t, that's the slope you get in this direction. Rate of change with respect to y times delta y, that's the slope you get in this direction, times the distance you move in that direction. And that all gives you the change in the value of the function. And you're not going to deeply understand that right now, but just kind of get the image to at least make it plausible. Okay. So, all you have to do is know now how to calculate these derivatives, right? And that's really simple. Okay, so let's let f of ty equal, let's just say t squared times the square root of y. I think that's what we used the other day. Okay? Okay? Partial of f with respect to t, you just take the derivative of the t part, treating the y part as a constant. Because in the example we just did, if t goes this way and y goes this way, if you're looking at this direction, y isn't changing. Okay? So if you understand that, you have a little more understanding. But whether you do or not, the rule is simply, if y is treated as a constant, then what's the derivative of this? Well, it's 2t square root of y, right? And the partial of f with respect to y is t squared times 1 over 2 square root of y. So df equals partial of f with respect to t times dt. This is the rate at which f changes with respect to t, so it's going to be 2t square root of y dt plus t squared times 1 over 2 square root of y dy. Okay? Now, the relevance of this to differential equations is the equation df equals 0 is 2t square root of y dt plus, thinking ahead and putting it equal to 0, t squared times 1 over 2 square root of y dy equals 0. Right? Well, that's easy to rearrange. Didn't leave myself enough room, but it's easy to rearrange. Okay, I'm going to write it out as t squared times 1 over 2 square root of y dy equals 2t negative 2t square root of y dt, right? Well, if I divide both sides by dt, I'm going to have a dy over dt over here, right? So, dy dt is going to equal what? Well, if I also divide by this, I'm going to have 2t squared y over t squared times 1 over t squared y and all that, right? And that's going to come out negative 2, no, sorry, negative 4, because I got 2 there. Negative 4y over t. Okay? So that's a differential equation. There's your f of ty. You can do what we did before. As long as you avoid where t equals 0, right? That's where the whole thing breaks down. To the right of t equals 0, you can do this. To the left of t equals 0, you can do this. But you can't cross t equals 0. So if you're doing the incremental thing and you start at negative 1 with an increment of 0.1, you better not try to go past the y-axis. Make sense? Okay, so there's a lot of stuff you want to think about there. Now, the solution to this differential equation, well, solution just f equals c. C being a constant. Because derivative or differential being 0 means it ain't changing, right? The rate of change is 0. You know, change in f is always 0. So the solution to this equation the solution equation dy dt equals negative 4y over t is t squared y, t squared square root of y equals constant. Y equals constant over t to the fourth. For any constant.